Oh. Should I pick Emily among? Maybe she's not ready. Any other person who is ready?
They can raise their hands, those who are ready to. Please put up your hand if you want to give us an opening prayer.
Hey.
Girls, are you in class?
Joanne, your hand is up. Joanne.
Amber is also up for an opening prayer. Almighty Father, King of glory, I thank you so much for today. I thank you for the gift of life. I thank you for what we have been able to make it to this lesson, O King of glory. I pray that as our teachers teach us, I pray to understand everything that they teach us. I pray that that you give us good connection, and also that you give our teachers good connection so that we can listen to our teachers as they teach us, and I pray that we also understand everything that they teach us, O King of glory. I thank you for our teachers. I pray that you bless them and you also bless us and everyone who is in this lesson. In the mighty name of Jesus Christ, I believe I've prayed. Amen.
Amen. Thank you so much, Joanne, for that prayer. I want to welcome all of you for today's lesson. And my prayer and wish is that you had a nice weekend. And just like the prayers has been, that we pray for good connectivity. Teacher Milton is in the house. I'll be the lead teacher, Mr. Bima. And we're picking from where you stopped last time. I understand you completed the topic, the subtopic of transporting plants. And before I go, I introduce the subtopic of transporting animals. I thought we would share a few things here. Then we briefly look at some of the questions that you had at the end in that slide, in those slides. This particular topic is an area that we normally have many questions in. I guide and encourage that when you are revising, there are things that you should be able to ask yourself when you are revising. There are things that you should pick from your notes as you revise, as you seek to understand the unit. For example, one area is the definition of the terms. If I were here, I'll just put this one somewhere. Definition of the terms used here. So you have a number of terms, whichever particular area you are revising, there should be some biological terms there. Like to do with osmosis, for example, what is it? Do we get it the way it is drafted in the text, in our notes? What is define osmosis, define active transport, define maybe diffusion, transpiration. So as you are revising, pick those key phrases in those definitions which must appear when they ask you to define. Another area that is will pick interest is in what is the importance of that term in the plants, in living organisms. What's the importance of osmosis? What's the importance of active transport? Then 3, just like in your notes, there are those questions that are drafted that will require you to describe an experiment to solve that. Describe an experiment to solve that. Probably transpiration occurs in a plant, or movement of osmosis in a non-living tissue, or osmosis in a living tissue. Whichever experiment is, I think we've said this over and over, the approach is the same. So in your description, there should always be a title of what you are going to describe, the purpose, the aim of that experiment. Then number 2, you should be able to list down the apparatus that you're going to use. Some people sometimes draw them and label them. It is cheaper to outline them. Just list down those apparatus. And then that will be followed by the procedure. What are the steps that somebody should be able to follow in order to carry out that experiment? All those relevant steps, you write them down. Some other times, some of those steps may be expounded by adding some explanations to a given step.
Teacher,
So
could you
do that.
repeat the first one?
I said under procedure, here you should be able to talk about those different steps that one should follow in order to carry out that step, or rather that experiment.
No, teacher, before you talked about apparatus, could you repeat what you said?
Oh, the first one under that is the title. Some people call it the aim. Some other times call it the purpose. What is it that you're dealing with here? So you say an experiment to show that. That will be you complete that statement. That will be your title. For example, an experiment to show that transpiration occurs in a plant. Or an experiment to show that transpiration occurs more on one side of a leaf than the other, maybe on the lower side of the leaf than the upper side. That will be your title. And then I said that once you have quoted, you have generated your title from the question. Maybe here, you generate that title from what the question wants you to do. So once you have done that, you go to the apparatus, the things that you need in order to carry out that experiment. So you list them down. And when somebody is awarding you marks, for example, if it is in a question, those different materials will be scored, will be awarded. And I said it is easier for you to simply list them down than to draw and label. And the drawing and the label may be more convenient to appear under the procedure. So it means under procedure, you could draw and label your setup. Then indicate things that cannot be drawn and labeled. Things to do with this, like things to do with the time, how long the time should be, and so on. Those ones you can use words to bring them out. But if you're poor at drawing, you can use words throughout, step by step, where you begin from at the time when you end with the experiment. And I was saying some other times the steps require that you add some bit of the reason as to why that particular step must be carried out. So all those must appear under your procedure. Then indicate, following the procedure, indicate the observations you're making out of that experiment. Before I forget, do not forget where there is need for time under procedure, put it there. Then your observations should reflect your procedure. So you should be able to indicate your observations. Probably 2 of them expected here. One is in your manipulation of the experiment. The second one will be relating to the control experiment. What if you removed that factor that you are talking about? What if you added that factor? So it means we expect kind of 2 observations here. Then from your observation, for observation, we expect that from your steps, from your procedure, you must have included a kind of a control experiment. Most of these experiments that we talk about, there must be some part that deals with the control experiment. So meaning that you're going to have 2 observations. One will be relating to the control, then the other one will be the investigation that you are carrying out. So those are 2. And it means somebody will be looking for 2 statements relating to the observation here. And then when we are teaching you, we bring in the aspect of explanation. The explanation, yes, in order for you to understand it. But in your description of an experiment, the bit to do with the explanation may or may not be relevant here. Then finally, you look at the conclusion, and I need to remind you here, your observation will be rather your conclusion will be correct and relevant when you make an appropriate observation. And you only make an appropriate observation when you are set up, when your procedure is correct. So it means where you fail in your observation because of wrong setting, then you don't expect to get a score for a conclusion. So the moment you,
Mr. Bima,
yes, sir.
Jovia says that we were left with a question last time.
Yes, Jovia. Jovia, are you still there?
Unmute and no, she says that there is a question they were left with last time.
Yes, I said we will. I will make these brief comments, and then we shall go through those questions, and then I will introduce the topic, subtopic that I'm supposed to.
Teacher, are you supposed to have an observation and a conclusion?
Precisely, that's what I said.
But don't they have the same statements?
No.
What's the difference?
The observations, so we want to talk about the results. Your purpose at the beginning was, so the 2 are not necessarily contradicting each other. So the 2 must be there. So you are talking about your observations, the stroke results. For example, if you want to show that, yeah, that's what I'm trying to do. For example, if they ask you to describe an experiment to show that more transpiration occurs more on one side of the leaf than the other, and then your results should be able to give you, or observations should be able to indicate that when you are recording your probably how much water is given from one side of this leaf than the other, in terms of maybe if you're using the cobalt chloride paper, and then you should be able to tell somebody that, prove to somebody that actually what you are seeing is that the cobalt chloride that you put on lower side maybe turns, is it red faster compared to the one on upper side. Then that observation is supposed to help you to draw your conclusion that, there is more water given, or water is given, there's a faster transpiration that occurs on probably lower side of the leaf compared to the upper side of the leaf. Once you're able to have this, most likely there could be other questions that will ask you to explain why you think transpiration occurs faster or more on the lower side of the leaf compared to the upper side, or the other way around, depending on your observations. So the conclusion must be there, the observation must be there. The observation stroke results must be there. Then allow me to finish my comment on the data. This is also an area where
Mr.
you,
Lee,
yes. Yes, please. Teacher,
well, also to add on something small.
Go ahead, please.
Yes, also to add on something small. Basically, the difference between the results and observation is that observation is what you see. When you carry out the experiment, what do you see? So what you see is the observation. Then the results is what you got. After carrying out your procedures, what did you get? Then of course the procedures, those are the steps that you went through to carry out the experiment. Like that, you can move on.
Okay. Thank you for that, Arthur, for making it a little clearer. Then the last comment I want to make is on how do you handle outside now, away from the description. This is another part. How do you, some other times we may be given results and we may be asked to generate graph work. So I want to inform you here that this is an area where you can be given questions in terms of numerical figures, which are actually results obtained by somebody. Then they will expect you to analyze those results by using graph work. So converting numerical figures into graph work, using the graph to interpret it. And in biology, we have a number of graphs that we normally use in order to help us help in the interpretation of the results that are generated. One of these is what was given to you last time, and where you are asked to draw graphs and generate graph on graph paper. There are some few things you should have in mind, and we shall go have the details some other time later. So your graph must have a title from your physics, mathematics. That graph you're going to draw on a graph paper must have a title, must have a scale, must have the axis. Then you must be able to plot. Then from the plots, you should be able to generate the curve. So those are things somebody will be looking for when somebody is looking at your graph work. The details of how you can generate the title, the scale, then the axis and so on, that will come later. But you needed to be, yes?
When you say the scale, do you mean that we should note down somewhere that, let me say, one box is equal to 5 centimeters or something like that? Like, should you note down, do they mean that you should draw the scale on the graph as you're drawing?
Thank you for that. I know you are ahead of the rest of us. And I say the details of that will come to you later. For now, in brief, those are things that you need to note down.
Excuse me, Mr. Song.
Yes, yes, please.
So I came late, so I'm confused as to what we're doing.
Oh, I was just trying to make some few comments because I know last week we completed the sub-unit on the transporting plants. I was telling your friends before you came in that this is a very good area where if you check through your past paper book, the name booklet, you realize there are so many questions that are generated from here. And I said, when you are revising through, there are some things that you need to take note of as you try to understand the sub-units. So I talked about the definition of terms that you find in your notes, importance of those biological terms like osmosis, active transport, and so on. Then I said, when you are revising, some other times you revise fine, but when we are doing bit of assessment or evaluation, and then you realize some other times you're given questions to do with the questions that expect you to describe an experiment. And if you go back to your notes, there are those aspects that are laid down properly. And I was trying to highlight on the approach required. That's like what appears in your notes. I'm trying to emphasize, in other words. So in describing experiments, I try to highlight what the components must be. Then you found us hinting on.
Excuse me, sir.
Yes.
But last time in the geography class, I wasn't here when we're drawing the graph, so I don't know.
Don't worry about the details of the components of the graph, but the major aspects that must appear on your graph paper when you're drawing are the title, the scale, the points that you're plotting, the axis, and then finally the curve. The different graph work here, we shall come back to it. Don't worry
Excuse
about
me,
it.
sir, I have
But
one more question.
Yes, please.
How does transporting plants have anything to do with the climate, sir? Because we were doing geography, now I'm hearing transporting plants.
Can I ask this?
This is biology.
This is biology. I'm not so sure whether you've been following it. Have you been
Oh,
attending
sorry,
the
sir,
lesson?
I thought this was geography.
May I know who is talking?
So it was polar. I understand what we're doing, so I just thought this was geography,
Okay,
so
it is
I was
okay. It is
confused.
okay. It is okay. Sometimes this happens. Now, can I welcome you to biology class now?
Yes, sir.
My dear, we're now in a biology lesson. Okay, is it okay now?
Yes, sir. Now I understand.
All right. Reorient your mind, and we're now for biology. So I say the details of how we can generate the title, the scale, the axis, and so on. We'll come to this at some other convenient time. Probably maybe we shall have one at the end of transporting animals. So I said that we marry. I thought I will share with you as we go into the assignment question that was given to you. If there are no more questions here, allow me to take you to Mr. Chebet. Mr. Chebet.
Yes, Adrian.
Allow me to share my slide, please. It is only the host. Give me the right.
Okay. Okay. It's fine. It's fine now.
Okay. You excuse me a bit. I'm trying to get to my slides. Mr. Chebet,
Yes, please.
can you share for me the slide on that's the last the revision questions on
But we are seeing them.
Oh,
We are seeing the revision questions.
okay, okay.
You have
Okay.
shared.
Yes, we can see them, Mr. Dino.
All right. Girls, I think that is what was given to you. Yes.
Now you're sharing explosions in Kampala.
It is on I think PDF.
Okay.
Okay.
There we are. We can.
So we have that. Of one lady, one girl to read for me the question. Teacher, better you pick for me.
Okay, first pause there, don't move.
One lady to read for me that question.
A freshly cut leaf. So do I read?
Please do.
A freshly cut leafy shoot was set up in a simple potometer made of a capillary tube. The number of minutes taken for the bubble to run over 15 centimeters in the tube was recorded with the potometer set under different environmental conditions as in the table below.
Recorded with it? Recorded with it? The
Recorded
potometer.
with the potometer.
Yes.
Set under different environmental conditions as in the table below.
Thank you. The assumption here is that we have some a mind picture of a potometer, and then we know how the potometer operates, and we're trying to use that in order to get the results here. So our table is giving us on right environmental conditions, and then on your left there's a time taken to run over 15 centimeters. So that is the time, rather the space over which a bubble of air is to move through the capillary tube. The standard that is being used here, as you measure the time taken. Then the lower one is giving us the rate of bubble movement in centimeters per minute. So how do we get the lower part? The lower part we got is got by dividing what we got up there. So time taken to run over over 15 centimeters.
Excuse me, teacher.
So we needed to calculate the first part in C and D, then fill in the table above. Can I get from somebody what your first figure was like under condition A?
Excuse me, teacher.
Yes, please.
When they say that rate of bubble, you have to divide, does it mean that you divide the environmental conditions over 15, or it's 15 over the environmental conditions?
Okay. What are the environmental conditions here? We have condition A, condition B, condition C, and condition D. We don't know for now what those conditions represent. But what we know, what we've been given is under condition A, for the bubble to move 15 centimeters, it took 60 minutes. Under condition B, for the bubble to cover 15 centimeters, it took 50 minutes. For condition C, for the bubble to move for 15 centimeters, it required 25 minutes. And then for under condition D, for the bubble to move for 15 centimeters, it took 75 minutes. Now here our minds will be, what are the possible environmental conditions? So in other words, your minds will go back to those factors that affected the rate of transpiration, which are environmental. There are those internal factors. There are those structural factors. So here our focus will be those factors that are outside the confines of the plant. For example, you must have talked about the light intensity. We talked about humidity. We talked about temperature and so on. Probably A, B, C, D could be reflecting either all of those or one of those. We'll try to suspect once we get our calculations. So you realize we are supposed to divide the distance covered by the time taken. That will give us the rate. The distance is constant, which is 15 centimeters. And then the time taken, which is variable in this case, depending on the condition, is what we divide it by. So I expect that we will divide for condition A, we will divide 15, which is the distance covered, by the time, which is 60 minutes. That should give us a figure like 0.25. And then we do the same for the rest. So for condition B, we are dividing the distance covered by the time taken. That will give us the rate. Change in the distance over change in the time. So the distance covered is the same distance, which is 15, divided by the time, which is 50. And then for condition C is 15 divided by 25. Then for condition D, it is 15 divided by 75. Can I hear your final computations for B, C, and D? Somebody who did that?
Teacher, for B is 0.3.
Good. C?
For C is 0.6.
Wonderful. D?
0.2.
0.2. Yes, just like what I said earlier, you realize that actually here we could have been asked to generate a graph work. But for now, we shall not dwell on that. So those are our figures. For A, 0.25, for B, 0.3, for C, 0.6, for D, 0.2. Those are the rates. What do you suggest will be the condition that is D? What kind of condition could D be? Could it be an environment with the high temperature? Could it be an environment with the high light intensity? Could it be an environment with the high pressure? So in other words, your mind should go to those environmental conditions, and then how those environmental conditions affect the rate of transpiration. I tried to generate a graph, only that I didn't transfer it here. You realize the rate in A, in B, and in D are more or less similar, around close to one another. A is 0.25, round figures is 0.3, B is 0.3, and then D is 0.2. So those A, B, C, and A, B, and D may not be very far from each other. So assuming we target them to high temperature, high wind speed, high light intensity, which one would it be? A, B, D, then C. Which one could it be reflecting high temperature, for example, high wind speed, for example? Can I hear that from somebody?
Excuse me, teacher.
Go ahead, please.
We're answering B.
Answering for?
Are we answering question B?
Yes, we are through with the question A. Then we are now on question B. What does the rate of bubble movement under each condition represent in this experiment? Can I hear the answer now?
Teacher, can I answer for C?
Go ahead, please. Hey,
I think
no,
C
we
represents-
first finish with the B. Let's first finish with the B. What kind of conditions could the A, B, C, D be representing? You remember they said those are environmental conditions. Can I hear from somebody? And why you think so? Go ahead.
I think C represents high temperatures.
C represents high temperature. Another condition that somebody could be suggesting here. I want to agree with you. C could be representing a high temperature. Looking at the figures, in other words, the rates under A, under B, and C, rather D, seem to reflect low rate of transpiration. Very high rate of transpiration seem to be depicted by C. So they're now asking us what kind of conditions are these where we have low rate of transpiration. Then we have, for example, under C, very high rate of transpiration. So that's what they want you to relate here. Can I hear some other answer, please? Teacher Milton, is there any other hand up?
No, I don't see any hand up.
Okay. So I will request you to answer part C. Let me suggest this. C, that's like what somebody mentioned, could be reflecting high temperature, could also be a condition of high wind speed, could also be reflecting a condition of high light intensity. Then the reverse could be true for A, B, and D. A, B, and D, the rates of transpiration there are low. Those could be reflecting conditions of low temperature, low wind speed. A, B, and D could be conditions of low temperature, could be a condition of low wind speed, or still air. And then it could also be a condition of low light intensity. Are we together?
Okay, there is a question here from Hope.
Go ahead. There's some who are said teacher. Let's give her the chance.
Hope has a question also.
Teacher,
the first one.
Why do you say low? Is it because of the rate of the movement? Because
okay. Let's go back to our figures. You remember the rates that we calculated? Let's go back to those figures under A. Under A, the rate under condition A is 0.25. Under condition B is 0.3. Under condition D is 0.2. Those are more or less the same or similar. Those are low rate of transpiration. Under condition C, we have 0.6, which we are suggesting here is high rate of transpiration. Now we are now asking question B is asking us what kind of condition is this where we have high rate of transpiration? What kind of condition is this where we have low rate of transpiration? And when you are looking at the factors affecting rates of transpiration, you mentioned you looked at the environmental factors, and one of these is the temperature, one of these is humidity, another one is is the wind speed, light intensity. Then you said under low light, for example, under low light intensity, the rate of transpiration is low. Now they want you to see if you can apply that concept in explaining this condition here. So if under low light intensity, the rate of transpiration is low, then moving backwards, what then happens if rate of transpiration is low? What kind of condition is light intensity? So we're moving backwards. So we're beginning with the low rate of transpiration relating to light intensity. So low rate of transpiration therefore occurs under low light intensity. And that is the condition D, B, and A. In a similar way, low transpiration which occurs in A, B, low rate of transpiration that occurs in A, B, and D occurs under low wind speed, because we know when speed is low, then the rate of transpiration is low because of the rate at which the bubbles are carried away. So we are beginning with the conclusion, then moving backwards to explain how those factors affect. Then the other question, Teacher Milton.
Excuse me, teacher.
Go ahead, please.
Teacher, I'm sorry to take you back, but I'm very confused.
Oh, go ahead with the question, please.
I don't understand anything that you are doing. Could you please go through it very quickly from part A, please?
Did you calculate in part A? Girls, let's not get tired because we need to move with everybody here. So when somebody is taking us to and fro, bear with us. And I request, where we are discussing something and you're not following it, please don't let us proceed with it. You ask, then say that we go together, okay? So let's go back to part A. Did you do the calculations?
Not
This particular lady, I'm not seeing her name here. Yes, who am I talking to?
Esther.
Who are you? I'm not, sorry?
Esther.
Yes,
Yes,
Esther. Did you do the calculation in part A?
No, I had internet disconnections.
Oh, sorry for that.
Yes.
Now, but did you have any
So
idea?
I also never got part A, if you can please repeat.
Oh,
I only
yes.
saw that table.
Do you see this table?
Yes.
Do you see what is on the right hand side of it, which says environmental conditions? Do you see what is on top of it there? Environmental conditions?
Yes, Mr. So we can see it.
Yes, you're able to see it. Now, do you remember those, when you are looking at the factors affecting transpiration, do you remember those factors?
Yes.
Can we go back quickly and pick your notes? Go to that that part that talks about factors affecting rate of transpiration. Very fast, go there. Environmental factors. Esther, are we there? And the other one who also came up said he didn't follow this. Quickly, let's go back. Someone who has seen them, try to read them for us. Environmental factors that affect the rate of transpiration. Can you read them to us?
Environmental factors that affect the rate of transpiration.
Yes.
Number one, humidity of the atmosphere. Should I read that?
Humidity. No, that's those particular factors. Humidity, that's one of the factors. Another one.
Temperature, light intensity.
Slowly, we're putting them down. Humidity, temperature,
light intensity.
Light intensity. Another
wind.
One. Wind. Another one.
Availability of water in the soil.
Yes. So let's pick one of them. Would you like to pick one of the factors and read for us how that factor affects?
Humidity.
Okay, let's pick temperature. Go ahead.
Temperature. An increase
Yes.
in the temperature causes an increase in kinetic energy of water molecules. This increases the rate of diffusion of water from the cell walls into the subatomic spaces, hence an increase in the rate of transpiration of the water vapor out of the leaf. An increase
at that
in
point. Slowly at that point. Let me pick some few phrases. An increase in temperature, you add for me the last phrase of that statement. Hence, an increase in temperature, hence,
an increase in the rate of an increase in temperature therefore increases the rate of transpiration.
Very good. It means at high temperature, the rate of transpiration is also high. Right? Right?
Yes.
And then it also means at low temperature, the rate of transpiration will also be low. Do we get that?
Yes, teacher.
Good. Let's go to the figures there. When we calculated the rate of transpiration, then we found those figures for condition A, for condition B, for condition C, and for condition D. Which of those figures gives us a high rate of transpiration? Under which condition?
Condition D.
Condition D? Is it D?
Yes.
High rate of transpiration?
C.
Yes.
Condition D.
Teacher, how is it D?
I'm also asking, is it D? Here in C, others are telling me B. For A, we got for A, let's move together. For A, we got a rate of 0.25. Are we together? Is everyone having that figure?
Yes.
And we got that by dividing the distance covered by the time, right?
Right.
Yes.
All right. So for B, we also did the same by dividing the constant distance, which is 15, by the time, which is 50. And we got 0.3. And in a similar way, we got 0.6 for C, then 0.2 for D. Are we all agreeing with those figures?
Yes.
Right now, which of those figures is the highest? That is now mathematics, 0.6. In other words, that means the highest rate of transpiration occurs under condition C. When you go back to those factors, like temperature, high rate of transpiration occurs at high temperature. Therefore, condition C must be a condition of high temperature. Condition C, in terms of light intensity, must be a condition of high light intensity. And then A, B, and then D must be conditions of low light intensity. Must be a condition of low temperature. Must be a condition of low humidity, rather high humidity, because rate of transpiration is high under low conditions of low humidity. So C must be a condition of low humidity. A, B, and D must be a condition of high humidity, because under that we have low rate of transpiration. So that is what we are generating from those figures. So the two ladies, I don't know whether we make meaning of those figures. Are we together, those two girls?
Yes, teacher.
I'm sorry, we are taking that bit of time because we need to move together here. We don't want to leave them behind. Therefore, in other words, yes, please.
I beg your pardon. You said that C has high light intensity.
C must be a condition of high light intensity, must be a condition of high temperature, must be if you're looking at it in terms of those particular environmental factors. So must be a condition of low humidity, must be a condition of low water available in the soil. But for the case where we're using the photometer, that condition of water availability in the soil may not now be may not apply here, because we're having a constant supply of water from the beaker that is provided. So in terms of temperature, in terms of light intensity, in terms of wind, in terms of humidity, we should be able to map those two conditions. Condition where C is a condition where A, B, and D are. So allow me to take you to C. Somebody that wanted us to wanted to give the answer to C. Could I go through?
B.
Through B, we're now saying condition A, from the figures we got, from the calculations we got, condition A, B, and D are similar conditions. Which the condition which is different is condition C, where we have high rate of transpiration, high rate of movement of the bubble. That reflects a high rate of transpiration. So the high rate of transpiration we're saying occurs under the condition which is high temperature, high wind speed, high light intensity. Can somebody add for humidity? Is it high humidity, low humidity for C? High humidity. Is that what you said?
Low humidity.
It is low humidity. Very good. So condition C is condition of low humidity. Then the opposite applies for A, B, and D. So A, B, and D must be a condition of low temperature, wind speed, a condition of low light intensity. Then in terms of humidity, what kind of condition is that?
High humidity.
Very good. So add it there. So A, B, and D must be a condition of high humidity in terms of one of those that you're looking at. So A, B, and D must be a condition of high humidity. Can we? Yes, please. Any other?
I got 0.6 for C.
Yes, I agree with you.
Okay. Teacher, is that how you submit?
Yes, we are using those figures to make biological meaning. 0.6, you're comparing it with the 0.25, or if you run that up to 0.3. You're comparing 0.6 with 0.25, 0.3, 0.2. You realize 0.6 is higher compared to 0.25, 0.3, 0.2. That's where we're making the conclusion from. Is it okay now?
I have a question.
No, the other lady first. You got 0.6 for C. We're making the meaning of.
Okay.
Is it okay now?
Yes.
Okay. Yes. Last question.
Teacher, I don't understand what the question B is asking for. Are they asking for what? For what? I don't understand what
the question is. What does the rate of bubble movement under each condition represent in this experiment? What does the rate of bubble movement? So the rate of bubble movement in A, B, and D is a low rate of transpiration. What does the rate of bubble movement under A, B, and D represent? That represents low rate of transpiration. What does the rate of movement of bubble in C represent? The rate of movement of bubble in C from our calculation represents high rate of transpiration. Am I with you now?
Yes, thank you.
All right, and then part C, somebody who had wanted to contribute there? Quickly, our time is running out. Somebody they had wanted to contribute here. Give at least 2 important precautions you would take when setting up the suit in the potometer to ensure that the apparatus works well. Anyone who attempted? Yes, please.
Teacher, when they say
Go
that
ahead.
shoot, do they mean like things that must be there?
Oh, I don't know. Let me take it back. I hope the figure is still here. The photometer. Do you have your printed work? Oh, yeah. This it's not clear.
You can move downwards. Mr. Bima, move downwards.
I move down. Oh, yes. Girls, do you remember on your left, you see a part of plant that is inserted. That is the suit that we're talking about here. So you cut it and fix it into what is that structure on your left. And then you have in the middle another structure which is carrying water. Then on the right you have a ruler attached to a capillary tube. So the measurements that were reflected in our data are got by using the distance covered here when we expose this to those different conditions that we talked about. So your question, going back to your question, can you repeat your question?
Give at least 2 important precautions you would take when setting up the chute in the potometer to ensure the apparatus works well.
Yes, this particular setup here, for it to work well. What are those things that you must have in mind? Yes, go ahead.
You should ensure that the plant does not take in air.
How do you ensure that the plant does not take in air? That is what we were interested in.
So the chute must be cut underwater to prevent air from entering and blocking the xylem vessel.
And from and what?
From entering the apparatus and blocking the xylem vessel.
You remember you are cutting the suit, and then you are telling us preventing air from entering the apparatus. Some of us are getting confused. The beginning part of the statement is correct. The explanation attached to it. Somebody to help you.
Pardon,
where are you? Yes, go ahead.
No, pardon, I think pardon.
Go ahead, please.
The chute should be cut underwater to prevent air from entering the plant.
From entering the plant. Which particular part of the plant are we talking about here?
The chute.
Then?
The xylem vessel.
Very good. So the first precaution is to cut this soot underwater in order to prevent air from entering the xylem vessels. What would have happened if the rather air entered the xylem vessels? What would have happened?
The air would block the xylem vessels.
So it will block the xylem vessels, therefore interfere with the uptake of water by the soot. Yes, that is the first one. We cut the soot underwater in order to prevent air from entering the xylem vessels, which otherwise would prevent uptake of water by the soot. The second one?
Can I try?
Go ahead, please.
The shoot should have many leaves.
No, I think we're about in the lesson because it's like 12:35, so I don't. Let's just wait and see what's up.
Are you talking to us or you're talking to the one who was given a chance earlier?
The shoot should have many leaves.
The shoot should have many leaves. What then happens if there are fewer leaves? Would you like to shed more light on that? What then happens if there are fewer leaves? Will the experiment work?
The calculations will not be accurate.
So,
So the water loss will be insignificant.
the water loss will be insignificant. To some extent, maybe, but I think there's a better option somewhere. Let's hear from another person. The second precaution. Somebody had talked about making sure that the setup is airtight, and we had asked her, how do we ensure that? And the answer didn't come through. Can I hear from somebody?
The stopper.
Yes, by using the stopper. So we make sure that when the suit is fixed onto the potometer, it is airtight by using the stopper. What else can we use if the stopper is not there? Or if the stopper is there and we still feel there is something that, sorry? We use a cork. Yes, cork, which must fit in family there. Then if not that, what else can we use?
Rubber.
Cork, rubber, doing similar work. What else can we use apart from
oil?
Stopper? Sorry, oil?
Mr. Abima, kindly requesting that we wrap up. The time is fast spent.
Okay. So we can have a stopper stroke. We could have a clay, some other times called China clay, in order to seal that off. So there are those two that we should have in mind. Then the last I think is straightforward. All of them. Question 2. Question 2. It is better to water plants in the evening than in the middle of the day. Can I assume these are straightforward questions, and then we go to my subunit? Girls, do you feel we go through them?
Yes. Yes.
Yeah.
Okay. Part A.
Yes.
Part A.
Yes.
It is better to water. Why do we think it is better to water plants in the evening?
Because in the morning, the water will be evaporated by the sun. While in the evening, the plants will absorb the water.
Yes, in the evening, there is a limited or little rate of transpiration that will occur. So we are avoiding that. And then part B, before transplanting a plant, it is a good idea to remove some of the leaves. That has a similar explanation, like for part A. Fewer leaves, we're reducing on the rate of
Transpiration.
Part C, water moves up steam more quickly on a hot day than on a humid day. Why?
Since on a hot day the temperatures are high, And transpiration also, the rate of transpiration is also high. So water needs to move quickly in order to support the rate of like photosynthesis and transpiration.
Then for the humidity?
For a humidity, the temperatures are low, so the water, the plant will need so much water.
On a humid day, we shall put it this way, on a humid day, there's already a lot of humidity in the atmosphere. So the atmosphere has less capacity to take up more vapor molecules. I repeat, on a humid day, there is already a lot of water vapor in the atmosphere. So it has less capacity to take up more water vapor molecules. On a humid day, there's already a lot of water vapor in the atmosphere, and hence the capacity of the atmosphere to take more water vapor molecules is reduced. Then for E, when a green fly,
Just thinking.
yes, E, somebody singing for us, thank you, not welcome. Part E, somebody to give us an answer.
So because it's the part where food is manufactured.
No, not manufacturing.
Yeah, food is translated.
Very good. It is through the flowing vessel that food is translocated. Then part F, water liquid may ooze out of the stump for a while. Excuse me. Please be kind to us. Don't sink in our lesson. That is in discipline. Yes, part F, please. Why do we see water oozing out of a cut stem? That is basically, yes, please, go ahead.
It indicates the presence of xylem tissue.
Presence of?
Of the xylem vessels.
I think there's another more precise answer. That indicates the presence of root pressure. Remember, root pressure pushes water. Root pressure pushes water up. Then part E, those ones I think you'll answer them. Of course, I need to have at least introduce my topic. Yes?
Let's take back and take a screenshot.
Yeah, instead of saying root pressure, can you say capillary?
Not necessarily. It is the root pressure that is pushed. Allow me to introduce the transporting animals.
Mr. Abim, I think we shall do that next time. The time we're already going to 15 minutes into the next lesson.
Okay. So, guys, I think we shall stop here. The questions generated more questions, and I think we needed them in order to grasp and understand more the units. So, thank you for your kind attention.